For this short session, what I want to do is look at behind two of the very important standards, U-value calculations and condensation risk calculations. Because we rely on these a lot, essentially, we're all familiar with the BRE U-value calculator, JPA, Build Desk. It gives nice slick outputs. The U-value is this, condensation risk is this, there might be some graphs in there, and it all looks fine. But I think it's really useful, because of how much we depend on those outputs, is to understand a bit more about what's behind them. So, what I'm going to look at is interstitial condensation risk, vapour permeability, the testing and terminology. I'm going to look at units, because we have some non-intuitive units like meganewton seconds per gram, so I'll try and explain where they come from. The combined U-value calculation, what exactly is it? How does it work? The BBA have a competency scheme for doing these calculations, condensation risk and U-values. So I want to highlight the things behind that, perhaps some of the gaps in those standards and the way we approach them, to give you a bit more of a understanding of these calculations when they land on your desks. We might say, well, why don't we measure in situ U-values, that is, U-values of buildings that are finished, which you physically measure. It's kind of possible, but it's immensely complicated. Look at cold roofs a little bit, the risks associated with those and how they're managed, and then some brief conclusions. Okay, so first is BS 5250. How does it work? It starts off with the assumption, of course, that we all expect, that warm air holds a lot more moisture than cold air. So there's a high vapour pressure inside the house, much higher than outside the house when it's colder. It's based on monthly, not quite monthly averages, but it assumes constant conditions inside and constant humidities for a month at a time. There's January, February, March, etc. And it assumes constant external conditions as well. This is a simplification. Obviously, buildings are not like that. They don't work like that. You might, perhaps it's helpful to try and understand why vapour does move through the construction, because you have this pressure difference. And you might recall your science teachers at school explaining about Dalton's law of partial pressures. Water vapour at atmospheric conditions behaves pretty much like an ideal gas. So you have a high partial vapour pressure inside. The essential point is that it's the distance between the molecules of water vapour and nitrogen and oxygen are so far apart they almost don't see each other. So it exerts a partial pressure, the vapour, which is much higher than the partial pressure outside. And that is the vapour drive. That is what's driving diffusion. And it is only looking at diffusion. It's not looking at moisture movement by convection through gaps and cracks. So it's worth bearing that in mind. Like many calculations and designs, it assumes perfection in terms of layer continuity, etc. And it is one-dimensional. As I said before, you might take, if you're doing a calculation for, say, Edinburgh, one of the colder locations in the UK, the 30-year average external temperature is maybe 3.5 degrees. And I've seen calculations using those figures, but that does mean that half the time, of course, the temperature will be colder. So BS 5250 recommends that you reduce those temperatures. Like for a dwelling, maybe you'd take a 1 in 10 year return, which would knock perhaps 1 degree off that. You can do like a 1 in 50 year return, which you might do for more sensitive buildings. The effect of doing a lower external temperature, of course, is to drag that temperature profile through the construction down. So layers in the construction that were previously above the dew point might now be below the dew point. And this obviously happens. This morning when I woke up, it was -1 degree centigrade. But if you look at the averages for Watford, it's not nowhere near 1 degree centigrade in this month. You know, it's 5 or 6 degrees. So that is a bit of a weakness in the calculation. It doesn't capture daily movements in temperature or very low temperatures. Now NHBC have like an unwritten rule of thumb to say, let's just take -2 degrees centigrade for a winter month and see what happens. Ideally, we don't want to see any condensation in the structure when the external temperature is -2. So this is giving adding a little bit more robustness, because to have no condensation, nothing in that fabric, no layers in the fabric are actually below the dew point. Now, the flat roof standard for many years, BS 6229, has advocated taking -5 degrees centigrade. This is obviously quite conservative, it's quite harsh, but it does happen. One of the main reasons for this is what we call clear sky radiation. Now, when you probably notice this effect without maybe realizing it, if you park your car outside your house one day and it's quite cold, maybe not freezing, but close to zero, and you might find you have condensation or ice on your windscreen on your car. You might notice actually that the part of the car that's facing a building or something might be free of ice. And this is what we call clear sky radiation, because the windscreen in particular is looking up at the sky. And if there's no clouds in the sky, it is looking at an environment that is at -270 degrees. So it's radiating loads of infrared radiation into a clear sky, and it's not getting much back. The effect of this is that that surface is going to be colder than the air temperature, and it can be quite a few degrees colder. If there is any kind of air movement, then that convective heat transfer will affect that mechanism quite significantly. But if you've got still air, clear sky, you can expect to see surface temperatures quite a bit below the air temperatures. And you can get black ice and things like this under these conditions. So it's not obvious, but there is the option of requiring that in your specifications and saying, well, let's take a robust external temperature. This does help also to some extent with convective moisture movement as well through gaps and cracks, because your construction will be more robust. The other aspect that affects your outcome of these calculations is, of course, the internal humidity. There are 5 humidity classes in the BS, starting with 1 which would be warehouses, storage, where there's not much moisture, going up to class 5, where it'll be swimming pools, breweries and stuff, where there's a lot of moisture a lot of the time. For dwellings, there are 2 classes, class 4 for high occupancy, class 3 for low occupancy. Now, I've seen calculations for class 3. Whether or not this is because going to class 4 would create a problem, I don't know. But I think you'll all agree that you can't necessarily predict what the occupancy of a building will be next year in 10 years' time. So it's much safer to assume at least high occupancy. It's a little bit more robust because there's a higher vapor pressure inside, and if it's low occupancy, it'll be safe. So 5250, the success criteria, what do you need to achieve? Firstly, in terms of surface condensation, or rather surface mold growth, you don't have to have surface condensation to get mold growth. You just need a high humidity. If the humidity exceeds 80% adjacent to a cold surface, external wall or roof for a significant period, that will allow mold to grow. So you won't necessarily see damp on the walls, but you've got the conditions for mold growth. The 5250 does allow interstitial condensation to occur, but there's 2 caveats. One, it must dissipate during the summer months, and secondly, you have to assess the impact of any interstitial condensation. That is, where does it occur, how much does it occur, is that likely to be a problem for the fabric that it's occurring on. There are places like in a cavity wall construction, in a vented cavity, where it's not going to be of any consequence because those cavities will expect to get wet anyway through rain permeating through the brick skin. So those are the three criteria that you need to achieve. So when we talk about breather membranes, etc., or even vapor control layers, how do we actually measure their resistance to vapor diffusion? And this is done using what we call the cup tests. Very simply put, it is a cup of desiccant or a salt solution that imparts a particular humidity above the surface. The test sample you're looking at is placed as a lid for the cup, as it were, sealed in. Then the cup is placed in an environmental chamber at whatever humidity, 50%, 90%, whatever. And the test technician will weigh those cups over a period of time. If it's a permeable membrane, it's every few hours. If it's a very high resistance vapor control layer or something, it might be weeks. But the rate at which those cups change their mass, they gain mass or lose mass, depending on desiccant or salt solution, is a measure of the rate at which vapor is permeating through that test sample. So you're effectively measuring the rate of mass change. You have a sample area for your lid, as it were, and you have a known difference in vapor pressure. So you're going to have this sort of outcome. You're measuring grams per second per square meter per Pascal. Pascal is equal to 1 Newton per square meter. It's a pressure. So when you substitute that in, you find the meter squared cancel out, and we're looking at the units that you see in the test reports you get from your insulation specifiers. Grams per second per Newton, or the inverse being resistance, Newton seconds per gram. So these are the common units you're going to see in these reports and in specifications. Water vapor resistivity, just the resistance of a unit of 1 meter thickness of material. That is obviously suitable for homogeneous materials like insulations. It's not suitable for something that's heterogeneous, like a foil-faced PUR board, because you can't say it has a particular resistance per meter thickness. It doesn't come in a meter thickness, and the foil, the PUR and the outer foil have completely different vapor resistances. So for those you would need to specify a vapor resistance for each layer in the construction. So foil, PUR, foil. Now, water vapor resistance factor, mu value, is also commonly used as an input on these calculations. What this means is that if something has a mu value of, say, 50, what we're saying is that its resistance to vapor transmission by diffusion is 50 times the same thickness of still air, where diffusion through the still air is only by diffusion, not by convection. So you might find a low density mineral wool has a mu value of 5 or something. It's about the same as air. Now, equivalent air layer thickness, SD, is another parameter we see, and this is saying the resistance of this material is equivalent to X meters of still air. And again, still air is a theoretical concept because you won't get still air, there'll always be convection. But have we heard of Intello being 0.25 meters up to 20, 30 meters? That's what it's saying. It's a relative measure, no dimensions. When we do come to these smart or intelligent membranes, of course, we have to look at the vapor resistance not under one set of conditions, but under a number of sets of conditions. And this would be on control samples and on aged samples as well, because we need to know they're going to work not just in the first few weeks, but in 10, 20, 30 years as well. So those membranes require extra testing. U values, we rely on these U value calculators immensely. 6946 is the calculation method, 443 is the conventions. It's not perfect, it's simplified, it's arithmetic, it's not modelling. Some of us can remember the days where you didn't have to take into account timber bridging, etc. Well, that has changed with time. And this standard will change with time as well. It will become more sophisticated, but it is an evolution, not a revolution. There is good resources in the Scottish regulatory guidance, actually, in general, but in particular they have worked examples of U values, which is quite informative if you want to understand what is an upper limit, what's a lower limit, etc. There are corrections that should be made for gaps and cracks in constructions, which you should see in U-value calculations more often than you actually do, but they are there in the calculation method. Given the importance of these calculations, the BBA and TIMSA some time ago launched a competency scheme for these calculations. The software is the software, it's a calculation, it's arithmetic. That's not the issue as such. What is important is what goes in, what the inputs are. The thicknesses, the conductivities, the mu values and the materials. So what this scheme will do is, first of all, set some problem examples. So have your people calculate these and send us the results. Then we can pick out the inputs and say, well, this is not a standardized input. Where's this come from? Is it legitimate? Is it evidence-based? Or is it just something that is convenient to use? Then we will do a management systems assessment of the applicant's process to see how the calculations are controlled and managed, how mistakes are dealt with, and how learning is shared amongst those carrying out the calculations. If anyone wants to join that scheme, my colleague Banaz is happy to talk to you about that and show you how to start off the application process. It's useful, I think, to look out for the competent person mark, the BBA mark, on these calculations as well, because it gives you a bit more assurance that the calculations are perhaps not individually vetted, but there is an oversight to it, because we can't check every calculation, but we do random audits and we do office visits to check out calculations have been done properly. So having seen some gaps in the process, you might say, why don't we measure in situ? Now at the moment there's one, possibly two standards issued in the whole world covering in situ measurement of U values. That's ISO 9869. It uses a heat flux meters stuck on walls or floors or roofs, so it measures heat flux under real conditions. But as you can imagine, you don't have any kind of stability in those. There's no steady state. Everything is changing by the minute, by the second. You've got sunshine, you've got wind, you've got rain, and that's before you look inside the building, and you've got occupant behaviour, heating's going on and off. So there's so much going on at the same time, it's difficult to be accurate about those U values, and indeed the 9869 is quite limited in scope. You can't use it for something that has bridges in it. It has to be something monolithic. If the sun's been shining on it, it won't give you the right answers. So although a lot of heat flux sensor work is done, it's not covered by standards at the moment. It's more done by researchers and so on. There is some efforts being made to produce some standards or technical reports on how to do in situ U-value testing. Also the co-heating test for buildings, which quite a long test, quite complicated, but this involves heating up a house or a building to at least 10 degrees above the external temperatures and maintaining that for a period of some weeks and measuring the energy need to maintain that. There's a lot of information you don't get, but you do get a rough idea of how much energy is needed. You get a heat loss parameter out of it. But that is some way from being a standard. Cold roofs. A lot of our buildings have cold roofs, that is horizontal ceilings with insulation in, or perhaps not, and pitched roofs above. This is described quite extensively in BS 9250, so it's worth a look if you have time. But they observe that a lot of the air entering rooms in these buildings will leave via the cold loft, so it's taking moisture and heat through a ceiling into that loft space. So it's not just heat you're losing, but you're taking moisture into cold space where it could well condense and over time cause fabric damage. And this is for a typical ceiling, and there are differences between ceilings. If you could change that typical ceiling to a well-sealed ceiling and cut down that air transport from the space below to the cold space above by around 70%, you can save 8 to 10% of the energy consumption for that typical house. So it's a very significant heat loss mechanism. In this type of construction, we can't use the BS5250 method, which is also called the Glaser method, which is a simple one-dimensional diffusion-only model, which is fine in some circumstances, but not when the mechanism of moisture transfer is not really diffusion, it's about convection, gaps and cracks. Some 20 years ago now, BBA first started certifying breathable roof tile underlays, which promoted an advantage over traditional constructions in that you didn't have to put any eaves ventilation and ridge ventilation because the membrane itself is vapour permeable. Now, like any construction, there are things that can go wrong with this. We've had maybe 3 or 4 complaints about these constructions in the last 20 years, and generally they're all associated with things that haven't been done quite right. One of the big issues is if you have loads of constructional moisture in your building and you're in the middle of a first heating season, the amount of moisture that can get into a loft space is very substantial, and you might get condensation even if you have ventilation. So it's important that the dwelling below these ceilings is ventilated, water tanks are covered, and in particular the penetrations into the ceiling are all sealed. Loft hatches is a major source of heat loss and moisture ingress, and we saw earlier today how a small gap can allow a lot of moisture to escape. Continuity of jointing with walls, for example in a cavity wall construction, you're not allowing moisture in that construction to find its way into the loft space, so they have to be closed off. If you don't, you've got a constant supply of moisture from rain permeating through the brick skin into the cavity, and it can escape into the cold space and cause problems. And you could consider vapour control layers at ceilings as well. So, very quickly then, in conclusion, there is obviously a lot of benefit in minimising unplanned air leakage and having wind barriers on the cold side of insulation. And that's not just fibrous insulations, but rigid insulation as well, because when that's installed between joists or rafters or whatever, it's really done perfectly, and things change with time. Timbers shrink, gaps open up, and that is an opportunity for convective air movement to draw heat through the construction. These mechanisms are not really fully recognised by current assessment methodologies, and this is probably one of the things that is contributing to the performance gap, where the U value is this. In reality, it can often be noticeably worse than that. As I said, it's almost impossible to measure in situ with any real degree of confidence. It can be done, but it's very laborious and complicated. So we have to rely on the existing tools at the moment, which are the U-value calculations, condensation risk calcs. But bear in mind at the same time that all these other things are going on at the same time, particularly gaps and cracks, heat escaping through these gaps and carrying moisture with it. And that's the big takeaway, I think, to remember this and try and guard against it. So on that note, any questions, either now or later? My email address is here if you want to get in touch afterwards.